So this section in this series of videos is about the multiplication rules for probability and conditional probability. And this is one of the longer and more complicated sections because it talks about several different kinds of probability questions. So I want to start by just giving you a preview of some of the different kinds of questions we're going to be answering in this section. So in this chapter, you may have noticed there are a lot of questions in words, like word problems. And for those, it's important to read the question carefully and understand what it is it's asking. Sometimes that's the hardest part. Once you understand what the question actually is, then answering it is fairly easy, but you got to understand what the question is actually asking. So read the question carefully and pay attention to little words like and, or, not, if, at least, because they can have a big effect on what the question actually is. So reading and understanding word problems and questions in words is something you can get better with practice. And part of what I'm trying to do in these videos is to get you better at that. Give you enough examples and explanations that you know what to watch out for when you're reading one of these questions. So here are some of the kinds of questions that we will be learning how to answer in this section. And questions. Like, what's the probability that something and something else both happen? Like, what's the probability that if a basketball player attempts 2 free throws, that she makes the first one and the second one? And I could have reworded that with the word both. What's the probability that she makes both free throws? So if you see the word both, that is an and question. It means the first thing and the second thing are both true or both happen. And there might be more than 2 things. She might be making 3 or 4 or 5 attempts. And we want to know what's the probability that she makes all 5 of them. The first one and the second one and the third and the fourth and the fifth. So that's still an and question. Or we might ask, what's the probability that none are? What's the probability that none of her free throw attempts go in? The first one does not, and the second one does not, and the third one does not, and so on. We'll also be looking at what are called conditional probability questions, where we ask, what's the probability of something being true if something else is true? Or what's the probability of one thing happening if another thing happened? What's the probability of something being true given that some other condition is met? And we'll see at least one questions, where you see the words at least one in the question. What's the probability that at least one? Like if a basketball player attempts 2 free throws, or 3 or 10, what's the probability that at least one of them goes in? So to give you some more specific examples of and questions, these will all be examples of and questions. If a basketball player gets 2 free throws, what's the probability that she makes the first one and the second one? If you draw 2 cards out of a deck of cards, what's the probability that the first is an ace and the second is also an ace? That is, what's the probability that both cards are aces? If a family has 2 children, what's the probability that the older one is a boy and the younger one is a girl? That's one of the things that could happen. There's other things that could happen. They could both be boys. They could both be girls. The older one could be a girl and the younger one could be a boy. But here we're asking about the probability that the older one's a boy and the younger one's a girl. What's the probability that a randomly selected voter is a Republican and voted for Hillary Clinton in 2016? So notice that's a smaller probability than either one of them by itself. A lot of people are Republicans. A lot of people voted for Hillary Clinton. Not as many, some, but not as many, are Republicans and voted for Hillary Clinton. Now, when we were doing the or questions in the last section, we worried about whether the events were mutually exclusive. When we answer and questions, we have to worry about whether the events are independent. So what does that mean? Well, it's whether they have any effect or influence on one another. Does whether or not the first event has occurred have any effect on the probability, how likely the second is to occur? If the answer to that is no, there is no effect or influence, then the events are independent. If the answer is yes, then they're not independent, they're dependent. So hopefully that'll become clearer when we look at some examples. So here's an example. Event 1, a person owns a dress. If I just pick a person at random, that person might own a dress or they might not. Event 2, a person is female. That's another thing that might or might not be true if I just pick a person. Are these independent? Well, if they were, that would mean that whether or not one of those is true has no effect on how likely the other one is to be true. Like, if you know the person is female, that doesn't tell you anything at all about how likely they are to own a dress. But I don't think that's the way it is. I think that if I knew that the person was female, it would be a lot more likely that that person owns a dress. It's possible to own a dress if you're not female. It's possible to be a female without owning a dress. But it's more likely that somebody owns a dress if they're female. And it's more likely that they're female if they own a dress. So if I tell you such and such a person owns a dress, you don't know for sure that they're female, but it makes it more likely. So these are not independent. They do affect the probability of each other. Another example. If I ask you to pick a card, look at what you got, but then put it back in the deck and we reshuffle and then you pick again, those two picks are independent. Whatever card you got on the first pick has no effect on what you get on the second pick. What's the probability of the second card being an ace? Well, whatever the first card was has no effect or influence on how likely the second card is to be an ace, because whatever you got the first time, you just put it back in, you reshuffled, it doesn't affect what happened that second time. But if you pick a card and then without replacing it, you pick another card, then the two picks are dependent. Then what you got the first time does influence the probabilities on your second pick. What's the probability of that second card being an ace? Well, it depends on what the first card was. If the first card you picked was one of the aces, then there aren't as many left in the deck on your second pick. So it's less likely that the second card is an ace than it would be if that first card was not an ace. So we have two separate rules. The first one is for when the events truly are independent. If they don't influence one another, if they're independent, then the probability that both of them occur, that A and B are both true, would be equal to the probability of A times the probability of B. You just multiply the individual probabilities together. And if we're talking about more than two events, we still multiply the probabilities together. So the probability of A and B and C all being true would be the probability of A being true times the probability of B times the probability of C. So for example, if you flip two coins, or you just flip the same coin 2 times in a row, what's the probability of getting heads on the first and the second coin flip? Notice it's an and question. the probability of both coins coming up heads would be the probability of getting heads on the first coin flip times the probability of getting heads on the second coin flip. So that would be 1/2 times 1/2, assuming it's a fair coin. And 1/2 times 1/2 equals 1/4, 1/4. If you were working in decimals, that would be 0.5 times 0.5, which would be 0.25. So you have a 1/4 or 0.25 or 25% chance of both coins coming up heads. If you flip 3 coins, what's the probability of all 3 of them coming up heads? That means you get heads on the first flip and the second and the third. So we multiply 1/2 times 1/2 times 1/2. That comes out to be 1/8, or in decimal, 0.125. If you flip 12 coins, what's the probability that all 12 are heads? It's still an and question, but this time there's 12 things that we're multiplying together. Because we're asking what's the probability that the first coin toss comes up heads, and the second one does, and the third one, and the fourth one, and so on. So we would multiply 1/2 times 1/2 times 1/2 times 1/2 times until we got 12 of these 1/2s all multiplied together. Another way to write that would be 1/2 to the 12th power. And if you multiply that all out, it comes to 1/4096. In decimal form, that would be 0.000244. Next example, Bob estimates that he has a 70% chance of passing history and an 80% chance of passing English. Assuming these are independent, what is the probability that he passes both? Notice that word both. This is an and question. We're asking for the probability of passing history and English. We know the probability of passing history is 0.70. We know the probability of passing English is 0.80. So the probability of passing history and English, we would just multiply those together. The probability of passing history times the probability of passing English. 0.70 times 0.80 is 0.56. What's the probability that he passes history and fails English? Now, first of all, what would the probability be that he fails English? Failing English means that he does not pass English. It's the complement of passing English. So the probability of something not happening, remember, is 1 minus the probability of that thing happening. So 1 minus 0.80 would be 0.20. He's got an 80% chance of passing English, so that means a 20% chance of failing English. So that means the probability that he passes history and fails English would be 0.70 times 0.20, and that comes out to be 0.14. What's the probability that he fails both? That is, that he fails history and fails English. So we're going to be multiplying together the probability of failing history times the probability of failing, that is, not passing English. So that would be 0.30, 1 minus 0.70, times 0.20, which comes from 1 minus 0.80, and when we multiply those together, we get 0.06. Okay, I have lots more examples, lots more to talk about in this section, so be sure and come back for part 2.